Okay, good afternoon, everyone. I'm going to talk about the numerical and experimental studies of X-ray light field imaging systems. And it's in cooperation project with Imagine Optique. And light field is a novel imaging technology first developed during last 30 years. With one exposure, it allows to reconstruct the focal image stack and the 3D model of the object. It opens doors to many different applications, such as the neural activity recording, facial analysis, inspection system, particle velocimetry, and volumetric deep cell imaging. However, all these applications are developed in the visible light range. There have been very limited developments in the X-ray range. So our goal is to build X-ray light field imaging systems, in particular for biomedical imaging. Under this project, there have already been two other theses from our group. The one of Elena Longo brought the first attempt to prototype a light field imaging system in a soft X-ray range, the so-called water window. And the one of Charlotte Herzog tested different system configurations in visible light and mainly worked on the reconstruction algorithms. Built up on their work, my thesis focused mainly on the search of the adapted X-ray optics. And the related work will be presented following this outline. In the first part, we are going to talk about some basic concepts about the light field to build up a theoretical foundation. And in the second part, the work about two X-ray optics for the contribution of the light field imaging system will be reported. And in the third part, I will talk about the first impairment on the entire system. And in the end, we are going to conclude all the work included in this thesis. Let's start with the light field basics. In this part, we are going to answer these three questions. What's the light field? How to capture the light field? And what the light field can be used for? Firstly, I would like to ask you a question. Have you ever thought about how we perceive our environment exactly by eyes? In fact, our eyes detects a wealth of information carried by the light traveling in space. As showing, this is easier to realize at night. As shown in the picture taken at night, we can only see the part emitting light and the part reflecting light. And the basic idea of light field is to capture and describe the light at each spot, at each position and in each direction in space. More precisely, the light field tries to capture the spatial and angular information of light rays and the geometric optics. However, such light field information cannot be captured by the conventional camera. As we can see in the picture, the image formed by a conventional camera is actually an intensity integral over all the direction of rays. So what that means, after the acquisition, we lose the angular information of the rays. Now, so how can we capture the light field? The first option, it can be a multi-camera array. The direction of each ray can be distinguished by the different position of cameras. And similar to this option, the light field can also be captured by one single camera, but moved to different positions. And the third option is the panoptic camera. It consists a mean length and a micro length array. The micro length array is inserted in front of the detector. And compared to the first two options, the plane optic camera is more compact and is able to capture simultaneously the spatial and angular information of light field. Each ray captured by the plane optic camera is actually parameterized by 4 coordinates of its intersections with the 2 separate planes, the plane of the mean length and the plane of the micro-length array. And conventionally, the coordinates in the plane of mean length are used to represent the angular information, and the coordinates in the micro-length plane are used for the spatial information. And in brief, the light field captured by a plane optic camera can be considered as a collection of 4D plane optic functions. Here we are showing a raw light field image captured by a homemade plane optic camera. As you can see, the light field image is actually an array of micro-length images. And each pixel of a micro-length image can be regarded as a ray captured. And its angular coordinates are given by the pixel indexed inside of this micro-length image. And its spatial coordinates are given by the location of this micro-length image in the whole light field image. So now we will turn to the question, with the captured light field data, what can we do? Firstly, the additional angular information allowed us to track the rays back to another plane after the acquisition, and enabled the numerical refocusing. On the right, we are showing an example, the refocusing results reconstructed from the light field image we showed before. And the light field was captured with a business card behind a transparent ruler. And with the light field data, we can reconstruct the image focused on the business card. Here we can see clearly the numbers on the business card, and the numbers of the ruler are blurred. And on the other hand, we can reconstruct the image refocused on the ruler. Now you can see the change of the sharpness between the numbers. And in addition to the focusing, another important aspect of the plane of camera is the depth of field. The depth of field indicates the range of the object distance that can be well resolved on the plane of detector. And the depth of field closely related to the numerical aperture of the optics. The numerical aperture is the range that the optics can collect the light. And a small numerical aperture leads to large depth of field. As we can see on the left, the mountains far away from the camera are still clear in the image taken with a small numerical aperture. And conversely, the large numerical aperture gives a small depth of field. We can only see the flower nearby are sharp in the image taken with a large numerical aperture. For a conventional camera, its depth of field can be changed by physically adjusting its aperture. To a plane optic camera, this can be numerically realized, as there is a relationship between the micro-length image size and the size of mean length aperture. choosing part of the microlens image, the so-called batch, is equivalent to changing the aperture of the main lens. And for example, the image shown on the right is reconstructed with the small batch size. And we can see its depth of field is limited to the plane of the Spider-Man. We can't see clear the numbers 100 and 120. If we reduce the batch size used in the reconstruction, its depth of field can be extended to the plane of the number 100. On the other hand, the light field data can also be arranged according to its angular coordinates and render the multi-view image. It's like we are imaging the object from different angles. Accordingly, we can see the shift of an object between the images at different angles in the multi-view image. This is called by disparity, and the disparity reflects the depth information of the object. Taking two images in the same column, we can see the disparity, vertical disparity, the shift of this object vertically displaced. And taking two images in the same row, we can see the horizontal disparity. As there are numbers of different angles in the multi-view image, and the disparity can be measured from any two images. So the light field data contains rich depth information and allows 3D model rendering. Combine these properties of plan-optic camera with the penetrativity of X-rays, it allows us to reconstruct the images focused at different depths inside of an object and reconstruct a 3D model of the internal structure of the object. Compared to the most common X-ray 3D imaging technology, computerized tomography, which requires up to 1,000 projections, the X-ray plan-optic camera has several advantages, especially for biomedical imaging. Firstly, it's more convenient for immobile samples. And secondly, 3D imaging with less exposures doesn't only reduce the radiation damage to the samples, but also has the prospect of rendering 3D video of living samples. However, to transform the plan-optic camera from visible light to X-rays, the main problem we encountered is to find the alternative optical components for the refractive main lens and the microlens array. As the refractive index is close to 1 for all materials in the X-ray range, the refractive lenses focus X-rays very weakly. So, to address this issue, we proposed two X-ray optics, which will be presented in the next section, the phenolazone plate and the curved crystal. Firstly, we proposed a phenolazone plate-based X-ray plan-optic camera, which means we replace the mean lens and the microlens array by a mean phenolazone plate and a phenolazone plate array, respectively. The phenolazone plate focusing X-rays relies on the diffraction and its alternating transparent and opaque zones select the rays with a specific optical path difference to produce constructive interference at the desired focus. The diffractive optics Venanson plate has multiple foci and forms multi-order images. But usually, we only use the first-order image. As presented earlier, the planoptic camera relies on the dense microlens array to sample the spatial information of the light field. So, for each lens in the array, the size is limited. To a Venanson plate, the limited size results in the very low number of zones, which greatly reduces the imaging performance. In order to design a dense Venanson plate array with acceptable resolution, we numerically investigate the impact of the number of zones on the imaging performance of Venanson plate. We developed a simulation code based on scalar diffraction theory. We consider first only one single point source, and it with field distribution behind the Venanson plate can be regarded as the integral of all its secondary sources in the plane of Venanson plate. This integral can be calculated as a Fourier transform. The result of this Fourier transform is the so-called point spread function, PSF. And the object and the image of an object formed by the Venanson plate can be obtained by the convolution of the image predicted by geometric optics and the PSF of the Venanson plate. In addition, the integral varies. The convolution varies according to the coherence of the source. Here, we only consider two extreme cases: the fully coherent case and the fully incoherent case. Firstly, we are showing the simulation results and the fully incoherent case. There are images with a different number of zones. And the first observation is that the image can be formed by a Venanson plate with only 5 zones, but of low quality. And we can say the image quality improves with the increasing number of zones. To quantify the improvement of image, we plot the contrast versus the number of zones. We can see the contrast plot increases quickly in the small number of zones, and evolves slowly, then roughly reach a plateau with 27 zones. This plot gives us a general idea about the number of zones for a single zone plate in the array. Moreover, we compare the Venanson plate images to the images formed by refractive lenses under the same condition. If such refractive lenses would exist, and from the compare these images, we can clearly find there is a diffuse halo in the Venanson plate images. This is due to the overlap of different diffraction orders image. This effect will decrease the contrast of the first order image. Now we will turn to the fully coherent case. And we can observe the same evolution of the first order image quality with the different numbers of zones. But at the same time, the other diffraction order images become more intense than the fully incoherent case. Indeed, the overlap of different diffraction order images decrease much more the visibility and the quality of the first order images in the fully incoherent case than in the fully coherent case than in the fully incoherent case. And at current stage, from the simulation results, we designed two finite zone plates with a different number of zones. The number of zones are 5 and 40. They will be further experimentally tested in the future. And after the studies about the finite zone plate design, we will focus now on the design of the mean length. If you remember, it's the angular information that enables the 3D reconstruction of light field. And the sampling of angular information is achieved by the numerical aperture of the mean length. On the other hand, the 3D reconstruction quality can be quantified by a term of voxel. It's like the pixel to a 2D image. So there is a relationship between the numerical aperture of the mean length and the voxel. The lateral and the longitudinal size of voxel is inversely proportional to the numerical aperture and the numerical aperture square of the mean length. However, for X-ray optics, they usually have small numerical aperture, and their numerical aperture reduces with the increasing X-ray energy. So the smaller the reduce of numerical aperture will result in the elongation of the voxel, which means the loss of the quality of 3D reconstruction. And if we see closer in this table, compared to other X-ray optics, especially in the high X-ray energy range, the curved crystal seems to have a larger numerical aperture. So we propose to use the curved crystal as the mean length and suggest the curved crystal-based X-ray plane optic camera. The curved crystal X-ray imaging relies on the Bragg diffraction. The rays arriving on the crystal at the angle that satisfies the Bragg's condition will be scattered in a specular way. And this angle, this incident angle, is called as Bragg angle. The plot of the crystal diffraction response along different incident angle is called the rocking curve. And for a perfect crystal, the rocking curve is a sharp peak. And for an imperfect crystal, the rocking curve contains several peaks with a larger width. Moreover, double curved crystal can focus X-rays in two directions. In order to eliminate the astigmatism, the horizontal and the vertical curvature of crystal need to satisfy this equation, which leads to a toroidal crystal. And for a curved crystal, it has a focus circle, the Rowland circle. and its radiance is equal to the half crystal horizontal curvature. And limited by the Bragg condition, only the rays arriving around the center of the crystal can be diffracted, which leads to a small numerical aperture, and this effective diffracting area can be extended by granting the crystal surface along its Rowland circle. And this structure is called as Johansen geometry. So over all these properties, we finally decided to use a toroidal crystal with the Johansen geometry for the use as mean length. Summarizing briefly all the properties mentioned above, we can see the effective diffracting area of a curved crystal can be affected by several factors, such as the crystal lattice parameters, the internal irregularity, and the curvature of the crystal lattice plane, and the curvature of the crystal surface. In order to consider all these factors in the design of a curved crystal, we developed a ray tracing algorithm based on the vectors calculation. And with this ray tracing algorithm, we studied two cases that have already been analytically studied by Vitry. And we can see the simulation results agrees well with the Vitry's results. However, the simulation results is more asymmetrical. That is due to the high order terms that have been neglected in Vitry's calculation. And with this ray tracing algorithm, we verified the the two-direction focusing ability of the toroidal crystal. And we calculated its effective diffracting area. It's quite large compared to other X-ray optics. We also calculated the focal spot of the toroidal crystal is nearly a point. And in this way, we customized a toroidal crystal with the Johansen geometry made of germanium 400. The fabrication of this crystal is carried out by Saint-Gobain. As the deviation between the theoretical design and fabrication cannot be avoided, we first check the parameters of this crystal by a full-circle diffractometer in LPS. And the full-circle diffractometer is capable of rotating the crystal about 3 axes. And it measures the crystal parameters by scanning the crystal diffraction responses at different rotation angles. And we test 5 different positions around the center of the toroidal crystal. We performed 3 scans with different rotation modes. The omega scan, we measured the rocking curve, Bragg angle, and the horizontal radius of the crystal. And the key scan, we check the vertical radius of the crystal, and the theta to theta scan, we measured the lattice parameters of the crystal. Analyzing the measurement plots, we can find there have certain errors from the theoretical values for the crystal, but in general, the curvature and the lattice parameters of the toroidal crystal are basically consistent with the design. And more recently, we did the preliminary tests on the entire crystal. The experimental source is an X-ray tube emitting X-rays at 8 keV. And the source, the crystal, and the detector are placed in focus-to-focus configuration. The direction of X-ray beams is fixed, and the incident angle can be changed by the rotation of the toroidal crystal in the horizontal plane. All the crystals are illuminated, corresponding to a numerical aperture of 0.1. We scan the images or formed by the crystal at a different incident angle, and here we are showing a part of the images. The difference between each image, the difference of the angle between each image is only 0.005 degrees. And we can see a small change of the incident angle will introduce a noticeable change in the shape of the focal spot. And the intense focal spot appeared around the Bragg angle, but with elliptical aberration, which is a characteristic of astigmatism. And we can also see some tails of this on this focal spot that indicates the common aberration. And this scan images confirms the focusing ability of the toroidal crystal, and shows the importance of precise alignment in the curved crystal imaging. Besides the studies on the individual optical components, we also carried out the first experiment on the entire system. And this experiment is performed at in a synchrotron of Thèse in Germany. And the experimental energy is 11 keV. We used the two separate test chart as the sample. The core part of the experimental setup consisting of a mean Fernand plate and a 9x9 Fernand plate array is a Fernand plate based planoptic camera. And the image formed by the planoptic system was converted visible light by a scintillator and then captured by a PCO camera. We first show the raw images captured by the experimental setup. We can see several structures in these raw images, like the different orders images formed by the Fernand plate in the array. And we can also see the shadow in the center of each micro images. This is caused by the center stop of each micro Fernand plate. The formation of such images is illustrated by the optical path diagram on the right. It's more important to notice here is the large distance between two micro images, which result in an extremely low spatial sampling rate. To compensate this point, we adopt the stitching method in the imaging acquisition, which means we captured several images with the Fanzon plate array moved to different places. Then we combined all these images to fill the gap in the initial array. And on the bottom, we show a set of images reconstructed from the experimental data with a different stitching number. The improvement of the reconstruction images can be well seen in this set of images. And with the experimental light field data before the reconstruction, we need to precise them. It includes two parts: the enhancement of the image signal and the localization of the first order image. These operations are applied on the images at each stitching position. Then we combine all the outputs together to get the total light field image. With the experimental light field image, we test the numerical refocusing. The results are shown on the left, refocused at different depths. We can see from the first target, the target closer to the mean length. Clearly, the focus change. We can see the focus change from the numbers -2 and 2. It was blurred at the beginning, then it turned to sharper, then it defocused again. However, for the second target, the target further away from the mean length remains always blurred. Also, there are some thinner bars appeared at a certain depth, which looks like the effect of refocusing. Is actually the result of aliasing. We tested the numerical refocusing with a different light field data captured at a different object distance. However, from the same data set, we can only reconstruct the clear image of one single target. This is because the distance between these two targets blocked by their holders is about 1.3 millimeter, much larger than the depth of field of the experimental setup is about 0.1 millimeter. And moreover, we investigate the resolution in the reconstruction images. We measured 1 micron wide bar on the target 1, the first target, and the resolution is estimated by the PSF size in the image, and approximated by the FWHM of Gaussian function. We measured the resolution in the images not only reconstructed from the experimental data, but also the images reconstructed from the simulation data. And the results are plotted in the figure on the right. With the evolution of this plot, it confirms the focus change in the reconstruction images. And the simulation plot agrees well with the experimental plot. The best resolution achieved from the experimental data is about 470 nanometer. It is the the reconstruction distance 128.7 millimeter. And this reconstruction distance corresponding to the best resolution provides the depth information of the first target. This value we extracted from the focus image stack 128.7 millimeter agrees well with the experimental object distance of the target one. As we presented before, the depth information of the target can also be extracted from the disparity measured in the multi-view image. However, in our case, we have much fewer microlenses, but each microlens image is larger. This will lead to a poor quality of the multi-view images. So for us, it's more practical to measure the disparity directly in the light field image. In this way, the depth we obtained is about 129.1 millimeter. And this value is consistent with the results from the focal image stack and the experimental object distance. To conclude, for the purpose to transform the panoptic camera from the visible light to X-rays, we proposed the toroidal crystal for the use as the main lens and the photon plate array for the user as the microlens array. At the same time, we also performed the first experiment on the entire system and experimentally built the first hard X-ray panoptic camera. The experiment results demonstrated the feasibility of the light field imaging in X-ray range. Overall, the work of this thesis contributes to the development of X-ray light field imaging, mainly from the aspect of optical component design. And the work of this thesis brought several insights for the future work. Like, firstly, we will integrate the new advancement of the computer science, like artificial intelligence in the post-imaging processing to improve the quality of the reconstruction images. And for the designed optical components, they still need to be experimental validated. And to fully explore the 3D reconstruction ability of the light field in X-ray range, we need to test the full system with the volumetric samples. And we will also broaden the studies of the X-ray optics from the curved crystal and photon plate array to pinhole masks and multi-layers. And finally, the experimental comparison with other X-ray 3D imaging technologies will bring more explicit understanding of the 3D reconstruction ability of light field imaging in the X-ray range. And in the end, I would like to thank the people who contributed to the present work from the following institutes and companies, and also for the fundings from the project Voxel and Expose and SIF. And thank you to the jury members for reviewing my work. And thank you everyone for your attention.